This is the 17th lecture of the course MTH 204A for section B. Recall that in the last lecture we proved that if P and Q are two distinct primes where P is less than Q, then and if G is any group of order PQ, then we have if P does not divide Q minus 1, so then G has to be isomorphic to Z modulo PQZ. So, G is cyclic. Otherwise, there are two possibilities, either Z is the cyclic group as usual, or Z is isomorphic, either G is isomorphic to this cyclic group or it is isomorphic to this semi-direct product. So, here from the notation I deliberately dropped the homomorphism, because we have also there seen that that is exactly when we prove the uniqueness, that whatever non-trivial homomorphism we take up to isomorphism, this is not going to change. And in fact, in the proof of that, the fact which was crucial that like for odd ZQ, so this automorphism group of Z modulo QZ is isomorphic to Z modulo Q minus 1Z. This fact was crucial in the proof of uniqueness, because since this is cyclic, so it will have a unique subgroup of order P. Hence, whatever non-trivial homomorphism we take from Z modulo PZ to odd Z modulo QZ, the image will be same. Hence, by the isomorphism theorem, we obtain the semi-direct product will be isomorphic. So, this is the crucial fact behind that. I used that there, as you can see, but there I did not give any justification. Later on I realized that, and I think I should give you, like though these two groups are isomorphic, but the isomorphism is not so obvious. So, I decide to give you an outline how to arrive at that isomorphism. So, I would like to give you a series of simple exercises which will lead you to the proof. So, first of all, it is quite clear that, so for any n automorphism group of Zn, that it is isomorphic to the multiplicative group of this, right. So, this is the group of all modulo classes which are co-prime to that of n. That is quite clear, because a generator, because if I take a automorphism of Z modulo nz, then that should map class of 1 to some generator, right, because on the automorphism generator should go to generator. Therefore, it is clear that from in view of that, it is clear that this is this. So, this is the first exercise. So, it indeed also tells that in this case the automorphism group has order Q minus 1. However, it is not guaranteed right now that it is cyclic or not. So, let us go for that. So, the next exercise is this. So, it is a number theoretic formula, but however it follows from Lagrange's theorem. So, maybe use Lagrange's theorem. Okay. And then using that, we will let us prove that for any finite group, the following are equivalent. What are the following things? So, for every d dividing n number of elements x in G, such that x to the power d is 1, is that has order at most d. Again, for every d divided n, G has at most one subgroup of order d, one subgroup of order d. The third condition is G is cyclic. Okay. Basically, you have to show that from this condition, from the second condition or from the first condition, you have to conclude that G has an element of. So, okay. So, here let this be n. So, G has an element of order n. So, that it's and that exactly yields that G is cyclic, and in view of that, the fourth okay, I should here leather put. And now talk about the fourth exercise. The fourth exercise says that let F be a finite field So, for example, z modulo pz, where p is a prime, okay, z modulo pz, if it is a finite field, then its multiplicative group is cyclic. Okay. So, multiplicative group means it consists of all non-zero elements of that field, and as a corollary to that you can immediately see that in particular for any q prime q, z modulo qz is isomorphic to. So, this has order q minus 1 and cyclic, so it has to be isomorphic to this for q prime. Okay. So, through this series of exercises, none of them is difficult. We can prove this, and then of course once we settle this, then we know once we settle this, then the rest was as we have said earlier. So, that shows that when in this case we have exactly one nonabelian structure or group structure of order p times q. Okay. So, I used this last time, but I did not give any justification. So, this is how you can prove this fact. Anyway, now I think I should go back to the applications of Sylow's theorems, which I was discussing. So, okay. So, last time we proved that if a group of order 60, if it consists of more than one Sylow 5 subgroup, then that has to be simple. So, now what we are going to prove is that suppose G is a group of order 60 and G is simple, then so can we remember such an example of a group of order 60 is simple A5. So, this says that then G must so G must be isomorphic to A5. So, how to prove this? How to prove this? So, our strategy would be the following. We will try to find a suitable set of phi consisting of 5 elements on which G acts and the action is transitive. Suppose I can do that, then this action will yield a homomorphism from G to S5, right, from G to S5, and because of the simplicity of G, the option for the kernel of this homomorphism, the options are only trivial and whole of G. Whole of G means the map is trivial, that means the action has to be trivial, but since it has more than one element and the action is transitive, then that possibility is ruled out. Therefore, this map will be 1 1, hence image of G inside S5 will be a subgroup of image of G inside S5 will be a subgroup of order 60, and already we have classified all subgroups of normal subgroups of Sn, okay, when n is normal subgroups of Sn for n greater or equal to 5. So, all total we then immediately conclude that G has to be isomorphic to S5. So, our task is to find a suitable S consisting of 5 elements on which G acts by conjugation. Okay. So, how to find such a set X? So, earlier we have seen that G acts on the set of so if I fix a prime dividing order of G, then G acts on the Sylow subgroups corresponding to that prime, G acts on that set on conjugation. So, that means we will try to see whether we can assure that for some prime dividing 60, the number of Sylow subgroups corresponding to that prime will be exactly 5. This is what we will try to first see. If that we can do, then of course we do not have to bother about anything else. Okay. How to do that? So, let us see what are the orders of what are the divisors of 60. The divisors of 60 are simply, as we have already seen, 1, 2, 3, 4, 5, 6, 10, 12, 15, 30, 60. Okay. So, from this what can we immediately say? N2, what are the possibilities for N2? 3, 5, 15. These are the possibilities for N2. Similarly for N3, 4, 10, and I think no more. And then N5 is only 6, because N5 equal to 1 cannot happen because of the simplicity. N5 is 1 means it has the silo 5 subgroup is normal, but that cannot happen because G is assumed to be simple. So, these are the situations. Now, you see that if I can assure that N2 cannot be 3 or 15, then it forces that N2 has to be 5, and then I will be done. So, let us try to see whether we can do it or not. So, how to do that? So, first of all, let us work out with this possibility, can N2 be 3? So, if N2 3, that means G acts on a set of 3, G acts on the set of 3 silo subgroups, but G acts on that by conjugation, and then that leads a homomorphism from G to S3. So, since the action is transitive, so this homomorphism cannot be trivial, okay. But again, because of simplicity, then it has to be injective, but that cannot happen because this has less number of elements. So, this possibility has been now ruled out. So, the next possibility which is left to us is N2 equal to 15. Now, so here any silo 2 subgroup of G will have order 4, okay. So, if H is a silo 2 subgroup of G, H will have order 4, and suppose N2 is now 15, okay. Then you see there will be a problem, because like if no 2 silo 2 subgroups intersect non-trivially, if no 2 of them intersect non-trivially, then what will happen? So, each silo 2 subgroup being of order 4, it contains 3 elements of order 2 or 4. So, in any silo 2 subgroup, there are, apart from identity, there are 3 more elements. So, they are having order 2 or 4. So, each silo 2 subgroup is having 3 elements of order 2 or 4, and if no 2 of them no 2 such silo subgroup intersect non-trivially, then we will have 15 into 3, 45 elements of order 2 or 4, of order 2 or 4. Now, let us come to this situation where we have 6 silo 5 subgroups. So, each silo 5 subgroup has 4 elements of order 5. So, then we will further have 6 into 4, 24 elements of order 5. So, all these elements are inside G. Now, if we just add them, then it will exceed 60. Okay. So, that shows that if N2 is 15, then there must be at least 2 silo 2 subgroups which will be intersecting each other, which will be intersecting non-trivially. So, let H1 and H2 be silo 2 subgroups such that the intersection is non-trivial. So, that means H1 intersection H2 must have order 2 because they have order 4. So, must have order 2. So, let this be generated by X. Okay. So, both H1 and H2 are abelian because they are of having order 4. Hence, like X commutes with all elements of H1 and all elements of H2 as well. Therefore, so H1 union H2. So, what is the situation? this is H1, this is H2, in the intersection I have identity and X. So, here you have 2 extra elements, here you have 2 extra elements. So, all total the union has 6 elements. So, this union must be contained in the centralizer of X in G, because X commute with all of them. That forces that the centralizer must have order 6. Now, what are the possibilities for the centralizer? So, it has order exactly at least 6, and of course, it just cannot stop with that, because because these two is the union of these two is not a subgroup. So, in fact it will be strictly greater than 6, because centralizer is subgroup, it just cannot stop with this. So, therefore, for the centralizer we have the following possibilities: 12, 12, 20 or 60. Okay. So, now if the last one happens, that is, if the centralizer is having order 60, then that means the centralizer is whole of G, that forces H has, that means X commutes with all elements of G, hence X will be lying inside the center. So, the center is non-trivial, since center is a normal subgroup, so that challenges the simplicity. So, this possibility certainly cannot occur. Now, the next thing, if the order of the centralizer is 20, that means the conjugacy class of X has order 3 in view of the orbit stabilizer theorem. Hence, we obtain the action of G on a set consisting of 3 elements, namely the conjugacy class. And this on the conjugacy class, because they are orbits, the actions are transitive. So, again like earlier, that leads to a homomorphism from G to ST, a non-trivial homomorphism, which is a contradiction, because a non-trivial homomorphism has to be injective, but this has less number of elements. So, even this possibility is now ruled out. So, therefore, what we are left with is the centralizer having order 12. If the centralizer is having order 12, then okay, let me do it here. If the centralizer is having order 12, then I think you can see what all that means. Again, from the orbit stabilizer theorem, the conjugacy class has order 5. So, thus let take S to be the conjugacy class of X in G. So, on this conjugacy class we have a transitive action, it consists of 5 elements. So, as we have argued earlier, we will obtain an injective homomorphism G2 inside S5. Now, S5, the only normal subgroup of S5 having order 60 is A5. Therefore, that injective homomorphism establishes a bijection between G and A5. That finishes the proof. Okay. So, enough of applications of Sylow's theorems. Now, we will again get back to classifications of P groups. As I have already said that when the order is small, then one can classify P groups without much difficulty. In fact, in this course we will be classifying groups of order P square and P cube. For P square we have already done. For P cube let us do it now. So, this is in fact an application of semidirect product and its recognition theorem and all the relevant results we have proved regarding that. So, let me get into this. Groups of order P cube where P is a prime, where P is a prime. Okay. So, first we will show that given any P, we can construct 2 nonabelian groups of order P cube. Okay, we will show that given any P, we can construct 2 nonabelian groups of order P cube. When P will be odd, we can show that those 2 nonabelian groups will be non-isomorphic, but when P equal to 2, they will be isomorphic to D8. Okay. So, first let us do the constructions, and once we are done with the constructions, then we will show that when P is an odd prime, then any group of order P cube, non-abelian group, must be isomorphic to one of these, or one of those groups that we constructed. Okay, so let me first do the construction. So first let us start with this. So this is a group of order P square. Observe that any automorphism of this group, can easily be seen to a linear automorphism of this vector space over Z modulo Pz, that finite field. Okay, that's easy to see. So any vector space, any automorphism of this group can be viewed as a linear automorphism of the vector space, of this vector space over the field Z modulo Pz. So therefore it is quite clear that this is nothing but isomorphic to this. And what is the order of this group? We can immediately calculate. That is nothing but P square minus 1 into P square minus P. So that is nothing but P minus 1, P plus 1, and then again P minus 1. Okay, fine. So since P is dividing the order of this group, so therefore there is an automorphism of this group having order P. Okay, in fact here we can pick such an automorphism explicitly. So look at inside this general linear group. What about this matrix? This matrix has order P, right? This matrix has order P. So therefore the automorphism corresponding to this matrix will be of order P. So what is the automorphism? The automorphism corresponding to that is the following one, that any typical element, let us say AAB or anything if you wish, maybe XY you can write, XY or MN, the reason is maybe M comma N goes to, so how do we see it? Class of M is nothing but, so here, so what are the generators of this vector space? So E1 is nothing but 1 bar comma 0 bar, E2 is nothing but 0 bar comma 1 bar. Okay. So therefore coordinates of this will be M bar comma N bar, and hence once you apply this matrix you must have M bar, M plus N bar. Okay. This is the automorphism of this group, and since this corresponds to this matrix of order P, so this automorphism has order P. So this is explicitly we have constructed an automorphism of this group having order P. Now the rest you know, that from Z modulo Pz, so if we call this automorphism, let us say something alpha, now from Z modulo Pz to this automorphism group, if we map, so mapping the generator of Z modulo Pz to this automorphism gives us a non-trivial homomorphism from this group to this automorphism group, and as a result of this we obtain a semidirect product we obtain a semidirect product, and since the homomorphism is non-trivial, this group has to be non-abelian. So thus we have constructed one group of order P cube using semidirect product, and this group is called Heisenberg group over ZP. This group is called Heisenberg group over ZP. Well, So when we say the group, then we have to ensure some sort of uniqueness. Here you can see that this group has been constructed by means of choosing an alpha first, which is an automorphism or which is coming from out of a matrix of order P. So you may say that there could be multiple such choices. So in principle, for each such choice we are supposed to get a similar group by taking the semidirect product in this manner. So it's natural to ask whether those groups are isomorphic or not. Let me repeat that for different choice of order P elements in this automorphism group, whether the semidirect product that we are going to obtain, whether those semidirect products are isomorphic or not. So that's actually quite easy to answer, because if you see here, so you see that P doesn't divide this factor or that factor. So therefore the highest power of P dividing the order of this automorphism group is P, hence the silo P subgroup of that automorphism group has order P. So therefore whatever order P subgroup you choose, or whatever element of order P you choose, then the subgroups generated by any two elements of order P are conjugate to each other. Hence by this isomorphism theorem we see that this construction up to isomorphism does not actually depend upon the choice of alpha. Okay. So whatever matrix here you choose, the isomorphism group, the group that you are going to get, so whatever element you choose, the semidirect product that you are going to get is going to be same, or in other words, whatever non-trivial homomorphism you choose from Z modulo Pz to this automorphism group, whatever non-trivial homomorphism you choose, this object is going to be same up to isomorphism. So because of this uniqueness, it is legitimate to call this unique non-abelian structure in this situation as this non-abelian structure. So because of this uniqueness, this non-abelian structure, this unique non-abelian structure, is reasonable to give it some name, and that's exactly called the Heisenberg group of order Z modulo Pz. As I said, that it doesn't depend up to isomorphism, it doesn't depend upon the choice of the non-trivial homomorphism. Okay, and that's why here also we deliberately drop the homomorphism from the notation, because whatever non-trivial you are going to take, you are always going to get a unique. Whatever non-trivial you are going to take, you are going to get a unique non-abelian group. Okay, in this scenario. Okay, this is one construction. So here we started with a group of order P square, which is structurally Z modulo Pz direct product Z modulo Pz. So another thing that we could have started with, instead of taking like for P groups of order P square, we have exactly two choices. One choice is this, another choice is Z modulo P square Z. So we can also start with that, Z modulo P square Z. So the order of this group is nothing but P square minus P. So phi of P square. So basically this will be P square minus P, and that is exactly P into P minus 1. Here also you see the same thing, that P is dividing the order of this automorphism group. So by Cauchy's theorem or whatever you like, there exists a automorphism of this group of order P. As earlier, we don't even need to use that. We can explicitly, we will explicitly construct an automorphism of that order. So what you do is, you consider this. So it's enough to mention where it sends the generator to. So we consider the automorphism sending one bar to this generator of this group, and I leave this to check that this automorphism has order P, order P. Okay. And as usual, once we have obtained an automorphism of order P, then as earlier from Z modulo Pz, so if we call this automorphism, let us say something like this beta, so Z modulo P squared Z to sending the generator 1 to this automorphism beta, we obtain a non-trivial homomorphism, okay, non-trivial homomorphism, and that leads us to the following semidirect product. Again the question of uniqueness comes into the picture, and that is also the argument is similar to the previous one, because here you see that the highest power of P dividing the order of this is exactly P. So, the P subgroup will have order P. So, thus whatever non-trivial homomorphism you take, or in other words whatever beta you choose, so may not be this, whatever beta you choose, then the images, then the image of this under that homomorphism will be image, so the image of this under any two such automorphisms will be conjugate to each other. Hence, whatever non-trivial this homomorphism you choose, this what you are going to get is isomorphically they will be same. Hence, we can safely drop the homomorphism, the reference of the homomorphism from the notation. So, the upshot is even in this scenario we obtain a unique nonabelian group, which is isomorphic to this. Okay. So, thus we have seen this by taking the semidirect product of two copies of Z modulo Pz and one copy, and with that Z modulo Pz we will get exactly one nonabelian group, and similarly by taking Z modulo P square Z and Z modulo Pz we will obtain exactly one, we will, by considering semidirect product we can obtain one and only one nonabelian group. Okay. So, thus we see that we have talked about two nonabelian groups of order PQ. Well, I should tell you why these two groups are non-isomorphic. That is not quite difficult to see. So, for that let me just write it in the multiplicative notation. So, like in group theory we usually write groups with multiplicative notation. So, what we do is, if we write the generator of this Z, in the first case let us say the generator of the first copy of Z modulo Pz by A, and if we write down that by B, and if write this by X, then what we found that of course that group is generated by these three elements, that is quite clear, okay, that is quite clear, these three elements, and furthermore we have the following relations between these elements. So, what are the relations? So, we have to mention that how X acts on, so if we conjugate A by X, how it changes X and how it is changing B when you conjugate B by X. So, that is because the conjugation is exactly meant by considering this homomorphism, and right, if you remember in the semidirect product, once we do the identification, then phi k of H is nothing but kh k inverse. So, you just have to mention that how it is conjugating. So, in this case, so of course now this x a to the power p equal to b to the power p, a to the power p equal to b to the power p equal to x to the power p are identity, and with that A and B of course they have to commute. So, and then we have to mention x inverse is AB, that comes from this, and simply you just check that after this semidirect product how it acts on A. You see, because of that this two here the generators are being the coordinates are being added up. So hence that means in terms of generator it will be A times B, and so you just don't get confused. So here we have throughout used the additive notation. I am just writing everything in the usual multiplicative notation. So thus a typical vector here should be denoted by, let us say, the a to the power. So vectors in this space, let us say having coordinates I, j, in the multiplicative notation they will correspond to a to the power I, b to the power j. Okay. So now it is quite clear that how this acts. So this AB and x b x inverse must be B. So this group, this Heisenberg group is usually written by this. So right now this is just a way of writing this group and it bears no other meaning. Later on, maybe not in this course, later on we will learn the meanings of generators and relations, presentations. Then you will understand why we write and why we are writing this like this. Then you will learn. But right now this is just a way of writing down the group where the generators are there and the relations among the generators are mentioned. So from these generators and the relations we see that we can immediately capture all the necessary we can recapture all the necessary information, we can extract all the relevant information about this group. So this is how we write the first group. The second group similarly we can write. So there I have two things. So x to the power p, y to the power p square equal to 1. So y is the generator of this, y p square equal to 1, and then I have to say x y x inverse is y to the power p plus 1. Okay. So that is how we can write down the second group. Here also is just a notation. So the reason for writing this in this notation is what I am going to say, that in using these notations it's easier to write down why, easier to note down or put down why the groups are not isomorphic when P is 2. So let us take the former one in case of in the former one. So in the first one, for any I, j and I, j, k and n, by induction you can prove this. So this is just a routine verification by induction, hence I am leaving that to you. This will be simply a to the power n times I, b to the power n times j, plus the most important thing n into n minus 1 by 2 times ki, then x to the power nk. That you can easily prove by induction. So this is as left as an exercise, simple verification. So in view of this, it is now quite clear that if P is odd, then if you take n equal to p, see this will be p into p minus 1 by 2, p minus 1 by 2 is an integer because p is odd. So therefore then you can see each element, because a typical element here will be of this form, right, and therefore it shows that if we raise every element to the power p, it will be identity. So thus if p is odd, then the former, then 1 does not have any element of order p square, order p square, whereas in the second case of course it does have an element of order p square. So when P is odd, these two groups that we have obtained must be non-isomorphic. So again let me repeat, when P is odd, then by means of semi-direct products, the groups that we have constructed, they are completely non-isomorphic groups. Now the question is what happens P is even, that is P is 2. When P is 2, so the second exercise is for P is 2, both are isomorphic to. So this one is Z modulo 4Z semi-direct product Z modulo 2Z, so that is D8. Both are isomorphic to D8. In fact, that may not, like looking at this complicated expression, at a first sight it may be difficult to guess whether this how this becomes isomorphic to D8, because in fact like what is the how even it may be at a first sight it may be difficult to guess the element of order 4. So let me help you out. So in fact, in 1 I am using this notation here because in this multiplicative notation it is easier to write things neatly. So ABX has order 4, that you can immediately see, because then you will be left out with only B square. So then if you repeat that with itself, then only you will get identity. Okay. So thus by means of semi-direct product we have constructed two nonabelian groups of order P cube. When P is not equal to 2, then they are going to be different. When P is 2, then certainly then they are going to be same. Now we want to show the uniqueness, that is every nonabelian group of order P cube, when P is an odd prime, it has to be isomorphic to either this, that is the Heisenberg group, or this. Okay. Again let me remind you that the uniqueness part is already done. So if I can show that, well, let me do it here, then it's better, then it will be easier for you to understand once when I will explain further. So in order to show that any nonabelian group of order P cube when P is an odd prime is isomorphic to one of these, for that we need to do some work, we need to make some observations. So let's start our preparations. So let P be an odd prime. Let P be an odd prime and G be a group of order P cube, G be nonabelian. Okay. Then what about center of G? Center of G of course non-trivial, so it will have order P, P square or P cube. Now since G is nonabelian, it cannot be P cube. So if it is P square, then G modulo center of G will have order P, that is cyclic, and it's a, I think I assume that all of you must have seen this earlier, or if not you can do it now, that if for a group G, if G modulo ZG is cyclic, then G has to be abelian. So therefore it forces that this has to have order P, and not only that, furthermore this must be Z modulo PZ, direct at Z modulo PZ, because the other possibility is it's P square Z, but then again it becomes cyclic. Okay. So this structure immediately tells us that whatever x we take from G, x to the power P must lie in the center. This is what it shows immediately. And furthermore, also in this case the commutator subgroup of G is also ZG, because G modulo ZG is abelian. So the G prime will be either ZG or it will be a proper subgroup of that, but this has order P, and if G prime is trivial, then G has to be abelian, but that is not the case. So G equal to G prime. So from this we are now going to show that the following map phi from G to ZG defined as follows: phi of x is x to the power P for every x in G, we are going to claim is this is a homomorphism. Claim phi is an homomorphism. Homomorphism. So showing phi is an homomorphism, that's actually easier. In fact, it follows from a general observation regarding commutators, which you can find in Damit-Foot as an exercise, but however, let me just state that here, and it will be left to you as an exercise, because this is just a simple straightforward induction proof. So let me record it as a proposition for any group G. Group G, not necessarily P group. So this part holds for any group G, and x, y in G with the property that x and y both commute with the commutator x and y. So if this happens, that is a group G and x and y are two elements which both such that both of them commute with the commutator xy, then one must have the following. The following holds for all n. Then the following holds for all n. So what is that? Simply x y whole to the power n, x to the power n, y to the power n, the commutator yx, n into n minus 1 by 2. Okay. This you can prove directly by induction. Now let us come to apply this to our case when n is p. Now when n is p and p is an odd prime, you see it will be x to the power p, y to the power p, and the commutator to the power p times something. The commutator yx, the commutator lies in the center, therefore, and the center has order p. So therefore, when in our case this term will be just identity. So the rest immediately shows this is a homomorphism. So in view of this proposition, the claim is hereby established. Okay. So once the claim is established, now let us look at this phi only. The question is, what is going to be the kernel of phi? Observation. What is going to be the kernel of phi? So the kernel of phi, the claim is either this has order either p square or p cube. One might wonder why this so, then let us prove that. So if the kernel has order p, then what can we say? Suppose the kernel has order p. Suppose that the kernel has order p, then take any x outside the kernel. Okay. So if we take any x outside the kernel, then x must have order p square. Why? Because what are the possibilities of order of x? X is not identity. X cannot be p cube, because x is p cube means G will be cyclic, so in fact G will be abelian. So the order of x cannot be p cube. Order of x cannot be p either, because all the elements of order p are contained inside the kernel. Hence the only possibility is this is p square. Okay. So therefore this subgroup is nothing but, you see, 1 x, x to the power p, x to the power p plus 1, x to the power p square minus 1. These are all the elements in the subgroup. And clearly x to the power p lies in the kernel phi, okay, because x to the power p has order p. So hence the subgroup generated by that is contained inside the kernel phi, and the order subgroup generated by x to the power p has again order p. So therefore both of them have order p, hence they must be now same, fine. So this holds for any x lying outside kernel, and also this shows that this is contained inside this, fine. Now again, so this is a subgroup of order p square, therefore there exists a y beyond this subgroup, right. So since y is beyond this subgroup, y is also beyond the kernel because kernel is contained inside this subgroup, hence the previous analysis goes, that is for this y as well we will have kernel phi is y to the power p. So remember that earlier we have seen for any x outside kernel this holds. Now y is also outside the kernel, so this must hold, and that gives us the following thing, that x to the power p is equal to y. Okay. So what does that give us now? Let me write it here. This implies that y to the power p must be x to the power p times some j, right, and that implies y to the power p is some x to the power j times p. So these are both the y and x to the power j, when both are raised to the power p, they are same, therefore it shows that y x to the power minus j lies in the kernel of phi. Kernel of phi is again contained inside, we have there seen, okay, this, hence from this it follows that y must be in the subgroup generated by x. That is a contradiction because we have chosen y in such a way that is beyond the subgroup generated by x. Therefore thus it shows that this is not going to happen, hence the kernel is order either p square or p cube. So that is going to be the crucial observation for us. Now let us try to prove, let us finish off the proof of uniqueness. So as I said, now we are left with two cases. Case 1, we are left with two cases. The case 1 is kernel phi is having order p square. So this is having order p square. Equivalently, there exists an element in G. There is an element in G, there is an element in G having order p square, order p square, or again which is equivalent to say there exists a subgroup of G such that H is isomorphic to Z modulo p square Z. So the equivalence of this and this are obvious. So in order to say this, so if there is no element of order p square, then every non-identity element will have order p, right? Because there cannot be any non-identity element of order p cube. The group is assumed to be non-abelian. So if every non-identity element has order p, then every non-identity element goes into kernel phi. So the kernel phi will be whole of G. So that corresponds to the other case. Okay. So in this situation we are having a subgroup of this form. Now what about the intersection of this with that? Kernel phi intersection H. So H is having order p square, kernel phi is having order p square, okay, and H is going to have, since H is a subgroup of order, cyclic group of order p square, it is going to have an element of order p. So therefore the kernel will be, so the intersection will be non-trivial, thus the order is at least p. In fact it will be exactly p, because if they are equal, then that, since both of them have order p square, kernel will be a cyclic group of order p square, hence kernel will admit one element of order p square. But certainly the kernel cannot do that, because every element in the kernel p If it raises to the power p, then it becomes identity. So order will be exactly p. Okay. I hope the point is now clear. So when that is the case, that means there exist. So there exist y in the kernel. So there exists, let me do a kernel other than h. Denote this subgroup by k. Now it's natural to see h intersection k is trivial because k has order p. Okay, k has order p. So if the intersection is not trivial, then the intersection will have order p. Therefore k will be contained inside h, right? But the generator of k does not lie in h by our assumption. And of course hk, this is a subgroup strictly containing h has order p square, the group has order p cube, so therefore this will have order p cube, hence this has to be whole G. So h is normal right, h is normal because it has indexed the only prime dividing G. There is a k is a subgroup with these things, with these two things true, hence by recognition theorem G must be isomorphic to the semidirect product of h and k for some non-trivial homomorphism phi. It has to be non-trivial because G is nonabelian. So therefore thus you see that in this case G must be obtained by considering G must be obtained as a semidirect product of z modulo p square z and z modulo p z. Okay. G must be obtained by a semidirect product of z modulo p square z and z modulo p z with respect to some non-trivial homomorphism. That's what we have seen. So G must be obtained like this. G has to be of this form. And earlier we have seen that by means of a non-trivial homomorphism from z modulo pz to z modulo p square z, and then consequently taking the semidirect product. In this way, if the homomorphism is non-trivial, in this way we are going to get one and only one nonabelian group, namely this one. So in this situation we see that G has to be isomorphic to this. I repeat the argument that here we have proved if kernel phi is the power p map, if kernel phi is p square, then G has to be of this form. Which form? It is the semidirect product of a cyclic subgroup of order p square with a cyclic subgroup of order p with respect to a non-trivial homomorphism. Okay, that is what we have seen. It has to be of this form. Earlier we have seen that by considering the semidirect product of a cyclic subgroup of order p square with a cyclic subgroup of order p with respect to a non-trivial homomorphism, the one and only one non-abelian group that we are going to obtain is this. That is what we have earlier observed. Hence, therefore, in this case G has to be isomorphic to that. Okay. Let us do the other case, and with that we will finish this lecture. Let us do the other case. So the other case is pretty similar. So with that we finish the classification of all groups of order p cube, non-abelian groups. Well, you might ask what happens for abelian groups. For the abelian groups we do the classification by a general theorem called structure theorem for finite abelian groups. So far this is just the classification for non-abelian groups. Abelian groups will be dealt with later. Their classification problem will be resolved by using a general structure theorem. Okay, so let us do the second case now. What is the second case? Kernel phi is order p cube. That means every non-identity element has order p. So, as usual, since G is a p group, of course G will have admit a subgroup such that whose order is p square, right, because for p group corresponding to every divisor of the order there is a normal subgroup, and in fact in this case H must be of this form. Because H is a group of order p square, H cannot have any element of order p square, okay, because this says that every non-identity element is going to have order p, okay. So, as expected we will pick an element. So, the strategy is exactly similar to the previous case, and then denote k by this. Now, it's an obvious verification that H intersection k is trivial, because this has order p square, this has order p, the similar logic, just the verbatim repetition of this, and this also follows by the same old argument. Hence, like earlier, G has to be isomorphic to semidirect product of H and K for some homomorphism phi, non-trivial homomorphism. So, thus what we see in this case, if the kernel of the power map is the whole group, then G must be isomorphic with the semidirect product of the subgroup, which is the direct product of two copies of Z modulo Pz with another copy of Z modulo Pz by a non-trivial homomorphism. G has to be isomorphic to this with Z modulo Pz by some non-trivial homomorphism. Earlier we have seen that the semidirect, by taking semidirect product of two copies of Z modulo Pz and another copy of Z modulo Pz by means of a non-trivial homomorphism. So, the only in that way the only semidirect only non-abelian group that we are going to obtain is this Heisenberg group. So, that shows in this situation G has to be equal to that Heisenberg group. So, the argument is again like the line of argument is again that of the what we that of in the case 1. So, here also we found that G has to be an semidirect product of two copies of Z Pz with Z modulo Pz by means of a non-trivial homomorphism, and earlier we have seen in that way we are going to get one and only one non-abelian group, namely this Heisenberg group. So, G has to be isomorphic to the Heisenberg group. So, this finishes the complete classification of groups of order p cube, I mean non-abelian groups of order p cube. Abelian groups will be dealt later, as I said, and p is an odd prime. Now, I will finish this lecture just by saying a few things. Okay. So, let me again tell you that these are the, up to isomorphism, these are the only non-abelian groups of order p cube when p is odd. Earlier we have observed said that when p is 2, then these are isomorphic, both are equal to D8. So, this classification theorem, which is a complete classification for p cube, that does not hold for when p is equal to 2, because in p equal to 2 of course these two are going to be same, and on the same and on the top of that, if we remember that this group of quaternions cannot be written as a semidirect product of two of its proper subgroups. So, therefore, in order 2 we do when p equal to 2 we do have a group of order p cube, group of order 8, which cannot be obtained as a semidirect product of proper subgroups. So, this classification theorem that certainly does not hold, because they can't, I mean there is a group which cannot occur as a semidirect product of its proper subgroups. Okay. So, therefore, even the non-abelian classification of non-abelian groups of order 8 is to be done is to be dealt with separately, but apart from that singular case, for all other primes the non-abelian groups of order pq are now classified. And let me again repeat that these are the only two structures, one is the Heisenberg group, another one is this group. Okay. So, with that I will finish this lecture.